Okay, so we're back with study guide for module 11 and we're on problem 7. If the moon orbits the Earth because the Earth exerts a gravitational force on the moon, what is the equal and opposite force required by Newton's third law? So if Earth exerts force on the moon, then what's the equal and opposite force? So Earth exerts force on the moon, moon exerts force on the Earth is the equal and opposite force. Moon exerts force on the Earth. And that force is equal and opposite. Number 8 says, what kind of force is necessary for circular motion? That would be centripetal force. And give the definition of that force. Centripetal force is a force that is directed perpendicular to the velocity vector. So centripetal force is a force directed perpendicular to the velocity vector. So when something is traveling in a circle, their velocity vector is going like this. Their force and acceleration vectors are perpendicular, 90-degree angle to it, in toward the center of the circle. The force vector is directed. Let's see, number 9. What are the 3 principles of circular motion? So all circular motion requires a centripetal force. When force increases, speed increases, and when force increases, the radius decreases. Those are the 3. And when it says all circular motion requires a centripetal force, that doesn't necessarily mean that the force or that the motion has to go in a complete circle. Even if you're just in a car going around a curve, that curve, even though it doesn't go all the way around in a circle, it goes partially in a circle. And so centripetal force is required for your car to make a curved turn. And that centripetal force is actually provided by the friction between the tires and the ground. So all circular motion of any kind, even if it's partly circular, requires a centripetal force. And then force is directly related to speed and inversely related to radius. Then number 10 is a child twirling an airplane on a string, just like the lab that we're going to do in class. And it says, if the child increases the speed of the plane, will the string exert more or less force? So we know that speed and force are directly related. So when speed increases, force increases. So if speed increases, force is going to increase. And then on B, if the child keeps twirling at the same speed but allows the string to go out, making the circle bigger, will the string need to exert more or less force? So if we look back at number 9, we see that force and radius are inversely proportional. So when the string gets longer, that means the radius gets bigger, force is going to get smaller. So force is going to decrease here. Yes, Jojo got K-Nex and he's building stuff. You can show everybody the cat. Where's your cat? Go get your cat that you made. And then the question 11 says, what is centrifugal force? Centrifugal force is not any real thing. People talk about it because of the centrifuge, which is just a thing that spins around and can separate like blood plasma from blood cells and stuff. But centrifugal force is not a real thing. It's essentially just the effects of inertia. Because when you spin something in a circle, like a liquid in a tube, the particles are going to push toward the outside of the tube, and then the tube will be able to move them in that circle. But there's no centrifugal force. There's only centripetal force to cause circular motion, and inertia, saying when something is traveling, it's going to keep going in straight line motion unless something acts upon it, like say a test tube in a centrifuge is going to act upon this stuff that's trying to go in a straight line and make it go in the circle. Number 12 says, in the following diagram, a ball is traveling from point A to point B. Draw the velocity of the ball and the force it experiences at a constant speed. Okay, so we've got this circle. The ball is traveling in a circle. It's going from point A to point B. So here's A, here's B, here's the ball, I guess. So if it's going from A to B, I guess like if it started here at A, it's traveling along to B. It's just trying to give you the direction, which is kind of a strange and unclear way to do it. because it's a circle. But essentially what it's trying to say is the ball is going clockwise. Okay, so from A to B. And it wants you to show the velocity vector, the force vector, and does it care about acceleration? Well, does or doesn't. So when something is traveling in a circle, its velocity at any given point is tangent to the circle, meaning its velocity vector is pointed right here. Let's say this is the center of the circle. That's the radius of the circle. The velocity vector is always going to be 90 degrees from the radius. So if this thing is going clockwise, its velocity vector will just be tangent to the circle right at the point where it is. Force and acceleration vectors always point down into the center of the circle like this. So force and acceleration vectors are going to point in toward the center of the circle like that. Is that all that question asks? I think it is. Okay, so now we've moved out of gravity, well, still kind of in gravity, but kind of into a rundown of outer space. So if you want to take a minute and review the lab activity we did in Module 7, where we went to the dark room and shined light on the Earth and moved it around the sun, there's some applicable information in there that was just easier to cover when we were kind of doing that lab. So first one says list the inner planets and then the outer planets. And I just write this, Mercury, Venus, Earth, Mars, and those are the inner planets. And you'll have to write them out and spell them out on the test if you're asked. But I just can remember kind of the list here. And then there's the asteroid belt there, which we talked in Module 7 about how some people hypothesized that there once was a planet there that somehow got destroyed and became the asteroid belt, but we don't know. But people kind of put that out there as a theory. And then Jupiter, Saturn, Uranus, Neptune, I can't fit it, J, Sun, Jupiter, Saturn, Uranus, Neptune. And then when Pluto was a planet, there was Pluto out here. Pluto's questionably a planet, so, you know. The inner planets, Mercury, Venus, Earth, and Mars, are terrestrial planets. They're, you know, they have land like Earth does. And the outer planets, Jupiter, Saturn, Uranus, and Neptune, are generally gas giants, mostly made of light elements like helium and hydrogen. So, Pluto's terrestrial, if that matters, although we're not considering Pluto a planet. List of planets is number 14. Oh, well, we did them in order. Inner planets here, outer planets here. That's the correct order. Number 15, list the planets that have rings. All 4 of these gas giant planets have rings. Although Saturn's famous for them, the others also have them. It's just harder to see. Number 16, where are most of the asteroids in the solar system? In the asteroid belt located between Mars and Jupiter. There's an asteroid belt, that's where most of them are. Let's see, what causes an asteroid to become a meteor? So a collision with another object, comet, another asteroid, knocks it out of its orbit, and then it can begin to move toward another planet, or it just, I mean, when it's knocked out of its orbit, it continues going in a straight line, according to the law of inertia, Newton's first law. But that can put it on a collision course with another planet or another asteroid or another body, a comet or something. Let's see. Number 18, what are the 3 parts of a comet? I think this was the most missed question on the test last year. So there's a nucleus, a coma, and a tail. Oh, I remember. And number 19 says, what part of the comet's orbit has all 3 of those parts present? And only when it's near the sun are all 3 parts present, because the heat of the sun starts to cause some of the ice in the nucleus of the comet to form the coma and the tail. Hopefully that thing is still working. Okay, so the 3 parts are only, ooh, my goodness, my camera is malfunctioning. Hold on. Okay. No idea what's going on here. I hope we're still working. Okay, so the nucleus, coma, and tail are all 3 present when the comet is approaching the sun or near the sun on the way back. Are comets' orbits circular or elliptical? Just like the planets, comets have an elliptical orbit, although its ellipse is much more pronounced and elliptical than the planet's orbits, which are nearly circular. 21 says, where do physicists think short-period comets from? And that would be the Kuiper belt. The Kuiper belt is where short-period comets come from. 22 says, what causes gravity? According to Einstein's theory of general relativity. And that would be that mass bends space, so that straight lines appear as curves. And you can think of that like, let's say you're sitting on your couch, and a larger person comes and sits down next to you, and then you kind of like fall in toward a larger mass. Mass bends space. And so when you have something with a huge amount of mass, it bends space around it, causing everything to move in toward it. Just like you move toward a large thing that just sat down on the couch, or, you know, if somebody lays down in the bed next to you and they're bigger, you kind of roll in toward them. So general relativity tells us that gravity is something like that. 23 says, what causes gravity according to the graviton theory? And that would be an exchange of particles between things with mass. So particle exchange causes the other forces, as far as we can tell. They can't mathematically show that that's the case with gravity. And general relativity seems to work pretty well to describe gravity, so jury's still out on that one. I mean, the graviton theory kind of has that observed symmetry of the universe going for it, because the mass that describes gravity also is similar to what describes forces, where particle exchange causes the force. But general relativity actually works pretty well, so it seems like it might be true. And I'm actually going to attach a video to the email that shows some really neat experiments. If only I had a giant piece of spandex and a huge trampoline frame, we could do it in real life and an extra class period. But anyhow, there are some physics teachers that were coming up with an experiment to show how mass bends space, and how orbiting things around a mass bending space really tend to work out like the planet's orbits. And it's just amazingly fascinating to watch. So definitely watch the video I attach about that. And that kind of supports general relativity. But, you know, the graviton theory is also kind of interesting. I tend to go with Einstein. But we don't know for sure. So that covers, hopefully, all of the study guide for Module 11. And this should be the end of the first week's videos. So just the snow day is now covered if you've watched this far.